Okay, now we present a very short introduction to these two topics, linear algebra method and probabilistic method. So first we will start with the linear algebra method. So we start with a very interesting problem. Okay? So there was let's say this is the story that there is a town. Okay. And this town was quite strange, right? In the sense that the people of this town had a very strange hobby. Their main hobby was basically, making, forming clubs. Okay, so you form, clubs with a few of your friends you can find, and then arrange club meetings, on a weekly or daily basis. And then they don't do anything else. This is their main hobby. Now the problem was that the number of clubs started increasing, and because there is no restriction, you can have so many clubs. Even the same set of people will form several sets of clubs, right? And then you have this club meetings. And now when we have several club meetings happening, and then one person is present in several of them, then there is going to be trouble that he will say that we have to change the time, but then he will say that okay, you change from the other club, we cannot change the time. So this creates lots of law and order problems, because there are too many clubs, they cannot find a time to schedule meetings, and then people get into fights. So therefore there is a lot of law and order problems in the country. So what the city council decided, they decided, okay, let us put in some new laws to do something about this, to reduce the problems with law and order. Right? So they sat together and discussed. We need to come up with some rules. So first they sat together, the city council. Somebody suggested, okay, here is some things that we can try to do. Right? We will say that every club must have an even number of members. Okay, so every club has an even number of members. And then any two clubs must share again an even number of members. Then again they said that okay, this may not be good enough. So let us say that no two clubs can have the same set of members. Right? So then maybe we can hope to reduce the number of clubs. Right? So no two clubs can have the same set of members, and each pair of clubs share an even number of members, and every club must have an even number. So with this, the city councils hope that they can reduce the number of clubs, and then solve the issue once and for all, right? Because they don't want to deny them, the right to form clubs, because that is the hobby of people. And next time you want to get bored, you don't want to disappoint them too. So then, of course, with these new rules in place, they said that okay, our club town is now known as even town. Now we have the clubs are all even membered clubs, so therefore we will have it as even town. So this resolution was passed, and then they said, okay, let's see what happens now. Okay, so after some time, they realized that this is not going anywhere. I mean, it has of course reduced the maximum number of clubs that were there, but still the number was very large, and then they could not solve it. So the conclusion was that this did not help much, right? So can you think about how many clubs can be there with these restrictions, right? For example, suppose that suppose there were only 32 people in the town, then how many clubs can be there? Can you tell me the number of clubs that you can have with respect to these restrictions? Because people follow these rules, the number of clubs, each club must make sure that this is followed, and hence we can figure out what are the number of clubs if there are, let's say, 32 residents in the town. So only 32 people in a small town. Now how many clubs can be there? I want you to think about this and come up with any number that you can have. Okay. So think about it for some time and then get back to continue the lectures. Okay, so I say that there can be 65,536 clubs. I mean, are possible, including an empty club, okay, without any member. So, well, I mean, with at least one member, we can reduce by one. No, I mean, at least this many, right? I mean, of course, we don't know. There can be more or not, but we know that there is at least this many clubs possible. So why is that? This is a huge number, right? So to solve this, I am going to put a further restriction, right? Apart from the three rules, I am going to say that we say that okay, every club must also have the spouses of its members, right? Anybody, so everybody, like forming clubs are essentially adults, so we can assume that they are married, and then anybody who is joining a club, right, must also have their spouse, like husband must have the wife as well as wife must have the husband, etc. Right? So anybody must have their spouses also as members, which puts a further restriction, right? I mean, I cannot choose one person without choosing the wife also. Now, the advantage is that, like, of course, when you are putting only two persons at a time, the number will always be even, right? So, therefore, if there are 16 couples, right, there are 32 people in the country, then each couple can individually decide whether to join a club or to be part of a club, right? So there is a choice of either 0 or 1, right? Either they join or not join. So there are 16 of them, therefore 2 raised to 16 choices are there. So which means that there are 2 raised to 16 clubs are possible, right? With all these restrictions. And this, you will see that because people are joining, as these couples, the number will always be even, and the number of shared people also will be even, because if there is one guy, then his wife, or if there's a lady, then her husband, right, will definitely be there. So therefore, it can never be odd. The intersection can be never be odd. The total number can never be odd. So therefore, we satisfy all the conditions. And you don't need to have the same set, because we are talking about disjoint. I mean, not disjoint, like distinct sets here. 2 raised to 16 distinct sets of couples are there. So therefore, we have 65,000 plus clubs already. Now, this you can see in a town with 32 people, there are 65,000 clubs. It's not going to help with the law and order, right? So, what do the city council do? Okay, they sat another time and then decided, okay, what to do now. So then one of the members said that, okay, maybe it's time we talk with some mathematician and then ask his help to do something about this, because the way we discussed and decided the rules, it's not going to be any help, it seems. So then he talked to a friend of his, and then with a mathematician, and then he said, okay, well, I looked at your roll book, and then there is nothing much to change actually. You just change the first rule, where you said that you have every club has an even number of members to odd number of members. Okay, that's enough. And you can even throw away the third rule, right? Third rule says that no two sets have the same set of members. Okay, so that you don't need. You can just keep the first two rules with the small change in the first rule, where you change even to odd. So even every club has odd number of members. Any two clubs have even number of members, and then that's it. You don't need any other rule. So they were kind of skeptic. I mean, come on, like this doesn't seem to be any solution. He said that okay, let us try it out. So they changed the rules to 1 and 2, and then renamed the town to Odd Town. Right? Of course, because odd number of members in every club. Now one can see immediately why the third rule is not necessary, because the third rule says that of the even town. The third rule says that no two clubs must have the same set of members, right? Now, since a club has even odd number of members, you cannot have another set with odd number of members, because then these two will have an intersecting set which is odd, and therefore the rule 2 will be violated. So rule 2 together with rule 1 will imply that rule 3 is always maintained. So therefore that is fine. Now the question is that how many clubs can be there with this restrictions? Can you think about how many clubs are possible with the rule 1 and 2 for the odd term? So let me come up with a small example. Suppose there is 6 people in the town, right? N is equal to 6. Then I come up with several possible sets of 6 clubs, right? Okay, so here is an example: 1, 2, 3. Then 1, 2, 4, 1, 2, 5, 1, 2, 6. Then 1, 3, 4, 5, 6, and 2, 3, 4, 5. So these are all odd numbered clubs: 3, 3, 3, 3, and 5, 5, right? So the first rule is satisfied. What about the second rule? If I take any two of them, you can verify that there are precisely even number of members, right? So 1, 2, 3, 1, 2, 4 has 1, 2 in common. 1, 2, 5 also has 1, 2 in common. Then 1, 2, 6, again all these three has 1, 2 in common. Then 1, 3, 4, 5, 6 has 1 and 3 in common with the first one, 1 and 4 in common with the second one, 1 and 5 in common with the third one, and 1 and 6 common with the last one. Again 2, 3, 4, 5, 6 has 2 and 3 in common, then 2 and 4 in common, 2 and 5, and 2 and 6 common. Then with these two you have 3, 4, 5, 6, right, in common, and therefore they are all even intersection. And so for 6 people we have 6 clubs, right? But can be there more? I mean, I am coming up with 6 is not a proof that I cannot have more. Now, well, there are other ways of coming with several ways. For example, I can consider all the singletons, right? One person clubs, right? One guy, two by itself, 3 by itself, etc. 6 by itself. These satisfy again odd number rule. Then also any two has no empty intersection, therefore that is also true. So 1 and 2 are satisfied. Similarly, I can talk about if I start with an even number people, right, like 32 or 6, then I can talk about the complements of the singleton, right? For example, if I have 1, 2, 3, 4, 5, 6, I just look at the set without the 1, without the 2, without the 3, without the 4, without the 5. This again is odd in number, and then any two will intersect in even, because one person will be missing from exactly both, and then remaining will be even in common. So I can have several ways of making sets with the cardinality is equal to, let's say, n, where n is even, and if n is odd, maybe we have to well, again we can take the singletons, and therefore we still have at least n people, n clubs possible. Now the question is that can there be more than n clubs, right? Now if it is only n, then it's a huge success, right, the rule, because from 65,000 we are making it to just 32, because 32 is the number of people in that city. So the odd town theorem says that if in a city with n people, there cannot be more than n clubs under the rules of odd town. This is a huge improvement, right? So now how do you prove this? So if you can think about proving this yourself, spend some time on this. It's a nice question. So we want to prove that if the city has n people, then you cannot have more than n clubs if rules 1 and 2 of the odd town are followed. Okay, so here is the proof. So for that we will use some linear algebra. So let us just recall what's a vector space. So a vector space is basically a vector space or a field we are talking about usually. So the elements of field are called scalars, right? It's basically an additive abelian group. We know what's an abelian group, what's an additive abelian group. The operation is addition, and it's closed under the scalar multiplication. Okay? So any such thing with the additional properties of distributive laws of addition over the scalar multiplication distributes over the addition and multiplication, and associative with respect to the multiplication in the field. So if that properties are true, then we have what is called a vector space, and the elements of these are called vectors. And you must have seen several examples of vectors and vector spaces and linear algebra related courses. So a set of vectors, let's say v1 to vn, is said to be linearly independent, right? If and only if, let us take the the scalars lambda, right? So lambda 1, lambda 2, etc. are scalars. Then lambda 1 v1 plus lambda 2 v2 plus etc. lambda n vn is equal to 0, right? So there is a zero relation between these vectors if and only if all the lambdas are 0. So if at least one lambda is non-zero, you will not be able to get the 0 vector. So what are the examples of vectors in vector space? For example, matrices, right? Square matrices, or any type of matrices, like one by n matrix. Usually we see vectors this way. Like we have several examples, and then you can talk about the in geometry you have the the lines from point to a point, right? So that kind of you can put with the direction you can talk about that as vectors, right? So all these examples you must have seen, and then and then the scalars are elements from a field like real numbers, rational numbers, other fields like f2, right? Finite fields, fp for any prime p. All these things are examples of vector spaces. Now let us look at a proof. Okay, so we have the people and the clubs, right? So we have n people in the city, and then we have number of clubs, let's say, right? Now for every club, I define the incidence vector, right? So incidence vector is say that okay, whenever a person, so I will number the persons, let's say 1 to n, right? There are n people. So if there is 32 people, 1 to 32, 6 people, 1 to 6, right? Then we say that okay, if person I is there in the club J, then the the ith entry of the club J is 1, and if he is not there as a member, then the entry is 0. It is just the incidence vector of the clubs. So as you saw in the previous example, we have several clubs. So the vector corresponding to the club 1, 2, 3 is here 1, 2, 3. The third 3 positions are 1, and then the remaining 3 are zeros, right? Similarly, you have 2, 3, 4, 5, 6 is a club, and therefore, except for 1, everybody else is 1. And the first entry is 0. So these are the incidence vectors, right? Now, let us define the inner product of two vectors, right? As the if I take vector x and y, then the vector x has like you have several n components, right? So n people are there. So the n positions are there, which tells 0 or 1 depending on the person is present or not, right? So the inner product x dot y is defined as x. So it's a time by time product x1 y1 plus x2 y2 plus etc. xn yn. So xi is the ith entry of the vector x. Then we have the sum of all this. Now, because the elements of the vectors are from the field, so x1 y1 is basically an operation over the field, and therefore I can add them up in the field, right? The addition with respect to the field holds. So the inner product gives you an element from the field itself. So x dot y, x and y are vectors, but x dot y is a scalar. So the dot product or inner product gives you a scalar quantity with this operation. Now, if you look at vi dot vj, right? So vi and vj are vectors. So where vi is the vector for the ith club, and vj is the vector for the jth club. Now vi is a vector, so we have to look at the entries of vi, right? 1, 2, 3, etc. n. Now, what is this inner product? Well, this inner product, because it's a time by time product, if the same members are present, the corresponding times will be 1, right? So therefore that product will give 1, and then you will add up 1 to that. So basically it counts the number of people common to both clubs. So CA intersection CJ, the cardinality of that will give you the inner product VI dot VJ. So the incidence, the inner product of the incidence vectors gives the number of people who are common to the clubs. Now let us look at the situation, right? In terms of the inner product, can you write the rules of the odd term, right? So the odd term rules I can now write, because the VIV dot VJ if I take, if I is equal to J, then it's basically VI dot VI. So wherever the member is present, it will be 1, right? So for each member I will get a 1. So therefore it counts the number of members. Because a club has odd number of members, the sum will be an odd number. So if I is equal to J, I will have VI dot VJ to be odd. On the other hand, if I and J are distinct, then the common members is always even by rule 2. So therefore, we want the dot product to be even. So VA dot VJ is even if I is distinct from J. Now, the thing is that we can work over any field, and let us, because all the elements we are looking at in the incidence vectors are coming from either 0 or 1, right? It's binary letters. We know that we can work with the field F2, which has only 0 and 1. So the rules now I can write as, okay, VA dot VJ is 1 if I equal to J, because over F2, odd numbers become 1, right? Because modulo 2, right? F2 is a field with 2 elements, so everything is reduced to modulo 2. So therefore, whenever you have an even number, you will get 1. An odd number, you will get 1 as a reminder, and then when it is even, you will get 0. Therefore, VA dot VJ is 1 whenever I equal to J, and 0 I not equal. This clearly says the requirements of the odd term rule, right? So because any two clubs, the inner product is 1, then we have I equal to J, inner product is 0, I not equal to J. Then it should be the case that they have odd numbers in each club and even numbers in common between any two. So now let C1 to Cm be the clubs with the corresponding incident vectors V1 to Vm. So we want to prove that V1 to Vm form a linearly independent set under the condition star. Okay, so if they are linearly independent in a vector space, a set of vectors linearly independent in a vector space, then we know that they must be there cannot be more than the dimension of the vector space, right? So if the vector space has dimension n, you cannot have more than. Now, if you recall your linear algebra, if you take the incidence vectors, like the vectors of length n, right, over a field, then you will see that they form a vector space of dimension n at most, right? So because you can find n linearly independent vectors, because each let's say that each vector you take only one, the ith element to be non-zero and everywhere else 0, then you will see that such vectors, right, you can find n of them, will all be linearly independent, and you cannot write them as linear combination of the others. So when you say two vectors are linearly independent, if as we mentioned before, you cannot find scalars lambda 1 to lambda n, at least one of them non-zero, such that lambda 1 v1 plus etc. lambda vm is equal to 0. If that is not possible, then they are linearly independent. Now, in other words, if they are, they sum to 0, then we have to show that the lambda size are all 0. So that is the way to prove this. So let us take any linear combination, let's say lambda 1 v1 plus lambda 2 v2 plus lambda mbm, and suppose this is 0, right? Now, considering this equation, we want to show that lambda i's are 0, right, in this equation, no matter what the of course the VAs are there, so we cannot find any lambdas non-zero with the equation getting 0. So to prove this, let us use the inner product. So we have lambda 1 v1 plus lambda 2 plus etc. lambda mvm. Now take inner product on both sides of the equation with v1. So lambda 1 v1 dot v1, lambda 2 v2 dot v1, etc. lambda m vm dot v1. It is equal to 0 dot v1, which is 0. Right? 0 is the 0 vector. So now what is lambda 1 into v1 dot v1? v1 dot v1 is vi dot vi is 1 in the field f2. That's what we mentioned, right? Because the club rules are satisfied, it is 1 because we have odd number of people in the club. Now v2 dot v1, because these are two different clubs, the incident vectors, they should share even number of ones, and therefore they will sum to 0 under the field f2. So therefore for every other term you will get 0. So therefore lambda 1 into 1 is equal to 0. Therefore lambda 1 must be 0. Now we just did it for v1, but we could have taken product inner product vi for any I, right? Didn't make any difference. So therefore we will see that if I take product with vi for each I, the corresponding lambda I must be 0. And this is true for every lambda I. Therefore we see that all the lambda i's must be 0. So the dimension of f2n, right? F2n is basically the set of all n length vectors in f2, right? So the dimension is n. This is n. Is equal to n. We must have the number of linearly independent vectors, which is m, right? Must be less than or equal to n. So the number of clubs, because each the incidence vectors of the clubs are, we have shown that it must be linearly independent, and since the dimension is at most n, we cannot have more than n of them. So that is the proof that we cannot have more than n clubs with respect to these two groups. Now let us try to look at the case, go back to the even clubs and then look at that. But before that, I will present you a couple of homework questions. So we want to VM B vectors with n entries, 0, 1 entries. Now show that if these vectors are linearly independent over some finite field fp for some prime number p, then they are linearly independent over the field q. Okay. Now this is a nice exercise. It's a basically linear algebra exercise, not on combinatorics, but it will be very nice to look at this. It will tell you we could have worked with Q also, but we don't have to, because once we show it here, that is also true there. Now the second question is that suppose the city, let's say clerk, right? I mean the city council clerk made a mistake when he was typing the rules, right? So and then he switched the roles of even and odd in the rules 1 and 2. So rule 1 now says that every club must have even number of members, and rule 2 says that any two has odd number of members in common. Now then what happens? So the odd town is there, but when he typed, the mistake was there for these two. And then now what happens to the number of clubs if this was published, right, as the rules? Can you put a bound on the number of clubs under this new rules? Now going back to even town, we want a few more tools from linear algebra to be able to look at this. So let us say that u and v are in vectors in a vector space. We say u is orthogonal or perpendicular to v if and we read it as u per v if the inner product is 0. Okay, so the inner product 0 means that the vectors are orthogonal or perpendicular. Now given any subset of the vector space v, S subset of v, the S per is the set of all vectors in V such that S dot U is 0 for elements in S. Okay, so for every element in S, we want S dot U must be 0. So collect only such vectors U with the property that for every element of S, I mean its product with any element of S will give you 0. Now one can show that S per, which is the collection of such orthogonal vectors, is actually equal to the perpendicular of the span of S, and both S per and span of S per is a subspace of V, right? S is just an arbitrary subset, but S per is basically a subspace of V. Because linear combinations of zero vectors are zero vectors. One can verify that this linear combinations will give the span, and that is a span of any set of vectors is a vector space. Then if S is subset of T is subset of V, and T per is contained, then T per is contained in S per contained in V. This is something one can easily show just looking at the previous definition. Now here is a proposition: if U is perpendicular to itself, right? So all the vectors in U, right, multiplied with itself gives you 0. Then U is called totally isotropic. Okay, it's just a name. So set is totally isotropic. A subset of V is totally isotropic if it's perpendicular to itself. Now, if U is a subspace of V, then the dimension of U plus dimension of U per is equal to dimension of U. This is another result. We will not. Maybe we can show it. Let me see. Yeah. Maybe not. So a bilinear form over a vector space V is a map. Okay. Let's say beta takes elements of tuples of V cross V, elements of V cross V to field element, right? Such that the function beta is linear in each variable. Okay? What I mean is that beta of lambda 1 U plus lambda 2 V comma W is lambda 1 beta of U comma W plus lambda 2 beta of V comma W. Similarly, you can switch W and lambda 1 U plus lambda U V, you will get still similar results. Now, if beta of U is equal to beta of VU, then we say beta is a symmetric bilinear form, and symmetric bilinear form is called an inner product. So there are several inner products. We defined the standard inner product earlier, but now it's a little more general. Okay, so symmetric bilinear form is an inner product, and equipped with the inner product, we call the vector space an inner product space. And we say that the inner product space is non-singular if the metrics associated with the with the beta, right? Beta is basically a linear transform, is non-singular. Now, again, we will not go into details of this. If you are not familiar, just don't worry about it. We just need some of the statements to prove this. And when you want to look at this in further, you can read about this. Now, so let us prove the proposition that we had earlier, that if U1 to UK, let's say, is a basis for U, because U is a vector space, right? The subspace of V. Then an element of V is orthogonal to U, right? It's in U per. If and only if UI transpose Bx is equal to 0, where B is the matrix representation of the inner product. Okay. So now, if for any vector UI, right, we should have UI transpose B x must be equal to 0. Now this defines a system of linear equations, right? UA transpose Bx for each UI gives a collection of linear equations, and the rank of the system of linear equations is at most k, because there is at most k vectors in the basis, right? So therefore, at most k are there. So if you have only k equations, the rank of the system cannot be more than k, right? So therefore, the dimension of the U per is at least n minus k, because these are the vectors which are orthogonal. Now, dimension of V is n. That is the assumption, right? And then if B is non-singular, then we know that the rank must be equal to k, right? Because if V is non-singular, then there is at least one n cross n, k cross k submatrix you can find over this k equations, right? The matrix of this. You can find k cross k submatrix who has the whose determinant is not 0, right? And then dimension of U transpose is therefore equal to n minus k, because if k are here, then n minus k all must be, you cannot have more than that. Therefore, dimension of U perp is n minus k. Now, if U is perpendicular to itself, then U is a subset of U perp, right? Because U perp is a collection of all vectors which are perpendicular to U. So therefore, since U is perpendicular to itself, it is a subset of U perp. Now, dimension of U plus dimension of U perp is therefore equal to n, because from the previous observation. Now, because dimension of U perp is n minus k, right? And this two sums to n, dimension of U must be less than or equal to floor of n by 2. It cannot be more than that, because dimension of U is less than or equal to dimension of U perp, and the sum is equal to n, then dimension of U is less than or equal to floor of n by 2. So this is these are the things that we can immediately get from a linear algebra book. Very basic results in the first few chapters you see. Now let's get back to our event town. So if vi dot vi is equal to, for the cardinality of ci intersection ci, which is cardinality of ci, but now because ci has even number of members, this over is equal to 0 over f2, right? Now again, when I is distinct from j, vi dot bj is intersection of ci and cj, a cardinality of that, which is also even, therefore it's also 0 in f2. Now I think I should have written this as f subscript 2. Sorry about that. This is not the usual notation. It is f2. Right now, now we have the vector space is totally isotropic, right? Because we are saying that every vector here is perpendicular to itself, because the span of v1 to vm now is all perpendicular to itself, because vi dot vi is also 0, vi dot vj is also 0 for any case. So u is totally isotropic, and therefore the dimension of u is less than or equal to floor of n by 2, where n is the dimension of the vector space, right? Now, if the dimension of the vector space over f2 is at most ceiling of floor of n by 2, then you cannot have more than 2 raised to n over 2 elements over f2, right? Because every entry, right, in this vector, right, n positions, we can have either 0 or 1, right? And since we are saying that there can be at most n by 2 such dimension is at most n by 2, you cannot have more than 2 raised to n by 12. So that's a proof that you have at most 2 raised to floor of n by 2 clubs. Now, what is 2 raised to floor of n by 2 for n is equal to 32, which is 2 raised to 16, which is 65,000. So therefore, what we came up with right now, with the further restriction that every spouse must be a member of the club, it is not a real additional restriction. It does not affect, right? That will still allow us to make the maximum number of clubs under these rules. So therefore, even without the restriction, you will not be able to do better than that. So this is basically what I wanted to tell you about linear algebra method. It's very short introduction. We have not gone to eigenvalue spectrum or other tools from matrices or linear algebra itself. But you will see how, you have at least seen how to use linear algebra tools to obtain counting results, right? This was a counting question, right? Number of objects of a particular type.